The new images obtained from the James Webb Space Telescope have astonished scientists, revealing an unexpected reality about the universe. Instead of simply expanding our view of the cosmos, these images have exposed a disturbing truth: our ongoing understanding is insufficient to comprehend the possibilities of the universe in its infancy. The current theories regarding the universe's origins seem to be reaching their limits, compelling us to reconsider new hypotheses about its early stages. This raises the critical question of how the universe was shaped and why. These discoveries are challenging even the most experienced space experts. As a result, there is a need to investigate the true nature of the Big Bang and its continuously evolving details. It may be time to reassess the Big Bang theory itself, as popular belief has often misrepresented it. The Big Bang wasn't merely an explosion within pre-existing space, but was the very origin of space itself, unfolding about 13.8 billion years ago alongside matter and time. One of the key features in real science and cosmology is the concept of a singularity, a point where gravity becomes so intense that the curvature of spacetime becomes infinite. After billions of years since the universe's creation, we now observe that our cosmic home exists as part of a vast collaboration. For scientists, this represents a crucial element of the universe's existence, emphasizing its ongoing expansion. The universe doesn't simply wander into pre-existing space, rather space itself continues to expand as supported by traditional theories. The first stars are believed to have started shining approximately 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Age of the universe. This was the era when the first brilliant celestial objects gathered to form mature galaxies. However, the pace at which these galaxies developed remains a mystery. A significant breakthrough came in July 2022 with the James Webb Space Telescope's first images, which revealed various galaxies, some of which had already existed around 300 million years after the universe's birth. Despite being much younger than the galaxies we observe today, these early systems were considerably smaller and less massive, aligning with the scientific model of the time. In the early universe, the density of matter was insufficient to create galaxies as large as those we observe in the present day. The discovery began with 6 extraordinary redshifted bright spots detected by the James Webb Telescope, triggering one of the most significant cosmic mysteries of recent times. These newly discovered galaxies, although similar in age to previously recorded galaxies, appeared nearly as large as our Milky Way. This finding has sparked intrigue within the field of Big Bang cosmology. Upon analyzing a series of images taken with the telescope's near-infrared camera, scientists confirmed the presence of these distant objects using redshift data. They concluded that the light from these galaxies had traveled for over 1 billion years before reaching Earth. Consequently, these galaxies had already existed between 570 and 700 million years after the confirmed Big Bang event. This astonishing discovery challenges traditional cosmological assumptions, which predicted the formation of much smaller, less developed galaxies at this stage in the universe's history. Instead, the James Webb Telescope revealed galaxies nearly as large as the Milky Way, defying expectations. The gravitationally bound stars in these galaxies had already accumulated mass exceeding 10 billion times that of the Sun. One of these galaxies even showed signs of having a mass exceeding 10 billion solar masses. However, whether this hypothesis is entirely accurate remains unresolved. Even in this scenario, the mass present in the early universe would be much greater than expected, creating an even deeper puzzle. The discovered galaxies challenge nearly all traditional cosmological theories. Even if by some chance one of these galaxies is confirmed to be accurate, it would force us to reconsider our previous assumptions regarding the existence of these early cosmic structures. The density of matter in the early universe would have to be far higher than previously assumed. Another possible explanation is that these galaxies formed in a manner completely unknown to us. These discoveries are raising questions that demand a re-evaluation of the Big Bang theory. Many space specialists are frustrated with these findings, and their voices are often heard in scientific publications. Those who question current theories are often labeled as unorthodox or extreme. Nonetheless, it is clear that even experts who continue to defend the Big Bang theory are confronted with unanswered questions. These questions include fundamental concerns about how 13.8 billion years ago something could emerge from nothing. Could something truly emerge from nothing, or was there a trigger for this event? Or was it just a random occurrence? Stephen Hawking famously pointed out that the nature of time as we currently understand it began with a Big Bang. Thus, this process couldn't have been initiated by something else or caused by an external trigger. Similar doubts are raised about the uniformity of radiation and matter across the universe. No matter where we look or at what distance we observe, there is a similar distribution of systems, nebulae, and radiation across the cosmos. Modern scholars explain this phenomenon through the theory of cosmic inflation. However, other specialists have extended this idea, proposing that the universe has expanded in a turbulent manner. According to this theory, expansion occurred only in localized regions like bubbles, while other areas continue to expand indefinitely. This model raises the intriguing possibility that other universes could exist within these expanding bubbles, each governed by its own set of physical laws. This viewpoint suggests that our universe might not represent the whole of existence, but rather be just one part of a much larger and more complex structure. Within this framework, the concept of an eternal cycle of breakdown and rebirth for the universe is advanced. However, this is far from the only perspective in cosmology. In 1955, for example, an article was published in NASA's Big Time magazine suggesting that the universe may have never had a Big Bang and that it has always existed, possibly for an infinite period. In this interpretation, the expansion of the universe would be non-existent, with the ongoing evolution of matter giving the impression of gradual development over time. One of the more intriguing hypotheses emerges from the realm of quantum physics and string theory. Some tests have suggested that our universe and everything within it could be a projection or simulation from a higher dimensional reality. While this may sound like a plot from a science fiction movie, it has connections to the Kardashev scale, which measures a civilization's level of energy usage based on its ability to harness the power of an entire galaxy. If a Type 3 civilization existed capable of utilizing all the energy of a galaxy, it might have created an ideal simulation of a universe. However, confirming the validity of such a scenario presents a significant challenge. Exploring the depths of cosmology and the origins of the universe leads us into an area of great mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of existence, testing established theories and encouraging scientists to reconsider fundamental aspects of our understanding of the cosmos. As observational astronomy continues to evolve, instruments like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, promise to uncover even more of the universe's secrets. Future observations may provide deeper insights into the earliest moments of the cosmos, potentially offering clues about its ultimate fate and the fundamental principles that govern its ongoing evolution. Meanwhile, particle physicists remain committed to understanding the fundamental particles and forces that shape the universe. The search for extraterrestrial life continues to inspire both public curiosity and scientific investigation. Future missions such as the James Webb Space Telescope's analysis of exoplanet atmospheres could reveal biosignatures that point to life beyond Earth. As scientific exploration pushes forward, so too do philosophical inquiries about humanity's place in the universe. The search for answers about existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration will continue to drive discussions across scientific and philosophical disciplines. The expanding frontier of cosmology. The discoveries made by the James Webb Space Telescope, JWST, have reshaped our understanding of the early universe, challenging long-standing theories and opening new avenues of inquiry. As scientists work to reconcile these findings with existing cosmological models, new questions arise about the nature of space-time and the fundamental forces governing the cosmos. One of the most pressing issues concerns the role of dark matter and dark energy. These unseen components are believed to account for over 95% of the universe's total mass energy content. While dark matter is thought to provide the gravitational scaffolding necessary for galaxies to form, dark energy is theorized to drive the accelerated expansion of the universe. However, the discovery of massive galaxies in the early universe raises doubts about our current understanding of how dark matter contributed to early cosmic structure formation. Could it be that dark matter behaved differently in the early universe? Or does the JWST's data hint at an even more exotic explanation, one that challenges the very existence of dark matter as we currently conceive it? Some physicists propose alternative models such as modified gravity theories, which suggest that our laws of gravity need revision rather than introducing an invisible form of matter. Another challenge arises with the cosmic inflation hypothesis, which posits that the universe underwent a rapid exponential expansion in the first fraction of a second after the Big Bang. This theory was originally introduced to explain the uniformity of the cosmic microwave background radiation, CMB, and the large-scale structure of the universe. However, the JWST's findings suggest that the first galaxies formed much earlier and grew much larger than inflationary models predicted. If inflation occurred, did it proceed differently than we assumed? Or is there an even deeper unknown process at play?